Changing capacitance 1. Here we see what happens when we first modify the separation between plates, and then second, and this will be in a second video, insert a dielectric, which is just a fancy name for the insulator between the plates of the capacitor, into the space between those plates. We will use the equations below as justification for our conclusions. We've met all of these equations so far, and so let's see what happens when we change the separation of the plates from D to 1/2 D. So here's what we're going to do. We're going to charge up the capacitor. The dielectric at this point is air or a vacuum, with the dielectric constant having a value for those of essentially 1. Then, with the battery still connected into the circuit, we reduce the plate separation from D to 1/2 D. So we're going to push these capacitor plates together. When we push the capacitor plates together, what's going to happen to the new capacitance compared to the original? Well, if we look at equation 2 up here, you can see that if D becomes 1/2 of what it was, then the capacitance is going to be doubled. The equation that justifies this is going to be that epsilon naught times A divided by D. Now, what about the new voltage compared to the old? It's going to be the same, and that's because the battery is still connected to the capacitor plates. That's going to maintain a constant voltage there. What about the charge that is on the plates? Let's look at this equation right here, number 1. If the capacitance has doubled and V has stayed the same, doesn't that mean that the Q must have doubled? 2 more here. What about the electric field between plates? We have an equation for electric field. Sorry, it's not on the screen now. Let me put it back. There it is, right at the top there in the middle. Electric field is E. Multiply that by the distance and you get the voltage. Well, the distance has become 1/2 of what it was, and we said right here that the voltage is the same as what it was. Put a 1 there. It's the same as what it was. So that must mean that the electric field must have increased to be twice what it was. So the justification that we're going to use there is this equation right here. And lastly, what happened to the energy? Well, we need some equation for energy. For a case like this, I like to use this one right here, because we can see that the charge has doubled. I'm going to put a 2 right there. And the voltage has remained the same. That's a 1. This factor of 1/2 is just a constant. We don't need to consider that. The point here is that the charge having doubled and the voltage being the same, that must mean that the energy has doubled. And incidentally, you could use either of those other 2 equations for energy as well. This one right here that's in the middle of the screen at the top, and then at the top right, that equation as well. If you work your reasoning skills around, you can figure out that, in fact, those equations also, based on what has already happened, show that the energy that we have stored now is doubled. So when we charge up a capacitor, leave it hooked up to the battery, we push the plates together, the amount of energy that's stored between the plates has doubled when we push the distance to be half of what it was. Now we're going to do the same sort of thing. We're going to charge the capacitor up again, but this time we're going to disconnect the battery, and then we're going to reduce the plate separation to 1/2 D. What's going to happen here? The distance between the plates has become 1/2 of what it was, and so right here, if I put a 1/2 there, if that's 1/2 of what it was, then once again that means that the new capacitance is twice what it was. This time the charge has to stay the same. Oh, let's put our little justification here. That's our justification. This time it's the charge that stays the same, and that's because the battery has been disconnected. The charge is isolated on the plates. It doesn't have anywhere to go. the total amount of charge can't change this time. Well, what does that mean? By the definition of capacitance, if the capacitance has doubled and the charge has stayed the same, that means that the new voltage is only half as much as what the old one was. And by the equation V is equal to E times D, if the voltage is half as much and the separation is half as much, then the electric field is the same as what it was before. And finally, what happened to the energy? Well, here's one equation for energy here at the bottom of the screen. And what happened to the charge? The charge stayed the same, and the voltage is 1/2 of what it was. So once again, this 1/2 right here that I'm circling, that's just a constant. That doesn't come into play when we're trying to figure out how has the energy changed by, because that 1/2 was there at the beginning as well. Whenever we want to know how much the energy has changed by, we look at what Q has done and we look at what V has done. Q has stayed the same, V has become 1/2 of what it was, so the energy between the plates now is only 1/2 of what it was.